Welcome to Civil Engineering Edge. Have you ever wondered why beams crack diagonally, or why stirrups are always provided near supports? In today's video, we're diving deep into shear stresses in RCC beams, a crucial topic every civil engineer must understand. From the basics of shear in homogeneous materials to his code-based design of shear reinforcement, we'll break it all down with simple explanations and whether you're a student, professional, or just passionate about structural design, this video will clear your concepts and boost your design confidence. So grab your notepad and let's strengthen your foundation in shear design. What are shear stresses in homogeneous beams? Shear stress in homogeneous beams arises due to transverse loads acting perpendicular to the beam axis. It is defined as the internal force per unit area acting parallel to the cross-section. In homogeneous materials like steel or plain concrete, the distribution of shear stress is parabolic, zero at the top and bottom surfaces and maximum at the neutral axis. This stress is essential in determining the beam's ability to resist sliding between layers. Understanding shear is crucial for the structural integrity of beams, as excessive shear can cause diagonal cracking or even structural failure in extreme cases. What are shear stresses in RC beams? In reinforced concrete RC beams, shear stress develops due to vertical or inclined loads. Unlike homogeneous beams, the presence of reinforcement alters the stress distribution. Concrete resists compressive stress well, but is weak in tension and shear, especially near supports where shear forces are maximum. The shear stress leads to inclined cracks, typically at 45 degrees, starting from the supports. These cracks are controlled by providing shear reinforcement like stirrups. Proper understanding and design against shear stresses are vital to ensure safety and durability of our C-beams under service and ultimate load conditions. Nominal shear stress. Nominal shear stress tau is the average shear stress in a beam section and is calculated using the formula tau equals VBD. Tau equals a frac VB. CDD tau equals BDV, where V is the factored shear force, B is the breadth, and D is the effective depth of the section. It does not account for the shape of stress distribution or reinforcement presence. Nominal shear stress is primarily used to compare the beam's capacity against permissible shear stress values given in design codes. If tau exceeds the design shear strength of concrete, additional shear reinforcement is necessary to resist the excess stress. Effective shear in RC beams. Shear force significantly affects the performance and safety of RC beams. High shear near supports induces inclined or diagonal cracks, especially in the web region. These cracks can lead to brittle failure if not properly reinforced. Unlike flexural failure, shear failure occurs suddenly without much warning, making it more dangerous. To ensure stability, shear reinforcement like vertical stirrups, bent-up bars, or shear links are provided. Proper detailing and spacing of shear reinforcement increase ductility and help redistribute stresses. Hence, understanding shear effects is essential to prevent premature failure and ensure long-term serviceability of our C-beams. Shear failure of a beam without shear reinforcement. When a beam lacks proper shear reinforcement and shear stress exceeds the concrete's capacity, failure occurs abruptly and diagonally. This is known as shear failure. Cracks originate near the supports and incline towards the compression zone, forming a brittle wedge. Since concrete alone cannot resist high shear, such failure is sudden with minimal deflection or warning. It compromises both safety and serviceability. This is why IS codes mandate minimum shear reinforcement, even when calculated shear stress is low. Preventing such failures through proper design and detailing is vital for structural integrity and user safety. Shear resistance of concrete without shear reinforcement. Concrete inherently offers some resistance to shear, primarily due to its compressive strength and aggregate interlock. according to is 456 to 2000. When shear stress in a section is within permissible limits, shear reinforcement may not be required. This permissible limit depends on the grade of concrete and is referred to as the design shear strength of concrete, denoted as tau c. However, this capacity is limited, and once shear stress exceeds C, shear reinforcement becomes essential. Without stirrups, any sudden increase in load can result in diagonal cracking and brittle failure. Even if the calculated nominal shear stress is less than C, his code recommends providing minimum shear reinforcement to cater to unforeseen stress concentrations, cracks, and redistribution. This approach adds a safety margin and ensures ductile behavior. Hence, while concrete can resist some shear independently, relying solely on it is not structurally advisable for durability and safety. Design shear strength of concrete? The design shear strength of concrete, denoted as tau c, is the maximum shear stress that concrete alone can resist without shear reinforcement. It depends on the grade of concrete and the percentage of longitudinal tensile reinforcement P. According to is 456 to 2000. Table 19. C values increase with higher grades of concrete and reinforcement percentages. The formula for calculating P is P equals 100 ASTB dP equals if frac 100 underscore ASTB dP equals BD 100 ast. Where ast is the area of tension steel, B is the breadth, and D is the effective depth. If the nominal shear stress tau is less than C, no additional shear reinforcement is required, though minimum reinforcement is still mandatory for ductility and crack control. If tau greater than tau C, shear reinforcement must be provided to resist the excess shear. For high shear stresses tau greater than tau K max, concrete is considered inadequate and redesign is necessary. Understanding to C helps the designer decide whether concrete alone can resist shear or if reinforcement is needed. It ensures safe, economical, and durable beam design, preventing brittle shear failures in real-world conditions. Minimum shear reinforcement as per his code. Even when calculated shear stress is within the concrete's capacity tau less than tau c, is 456 to 2000. Clause to 6.5.1.6 mandates providing minimum shear reinforcement in all RCC beams. This is essential for ductility, crack control, and to resist unforeseen stresses due to shrinkage, creep, or stress redistributions. The minimum area of shear reinforcement is given by ASVBS is greater than or equal to 0 for phi frac underscore SVB CDOTS JEC frac 0.4 F underscore YB SOV is greater than or equal to phi 0 for where ASV is the cross-sectional area of shear stirrups, B is the beam width, S is the stirrup spacing, and phi is the yield strength of steel, usually 400. Providing minimum reinforcement ensures that the beam doesn't fail suddenly and brittly under unexpected loads. It also helps in holding the concrete together after cracking, maintaining integrity. Therefore, even if shear demand is low, this reinforcement acts as a safeguard and must not be ignored in beam design. Maximum spacing of shear reinforcement, according to is 456 to 2000. Clause to 6.5.1.5. The maximum spacing of vertical shear reinforcement stirrups in RCC beams is governed to prevent large shear cracks and ensure uniform stress distribution. The code limits the spacing to 0.75D or 300 millimeters, whichever is lesser, where D is the effective depth of the beam. In members subjected to very high shear, the spacing may be further reduced to improve crack control. Additionally, when inclined stirrups or bent-up bars are used, their spacing is adjusted as per geometry. These limitations ensure that stirrups can effectively intercept diagonal cracks and provide continuity across cracked sections. Exceeding the prescribed spacing leads to ineffective reinforcement and wide shear cracks. Maintaining the correct stirrup spacing enhances ductility, toughness, and post-cracking behavior of RC beams. It's a key factor in both safety and long-term performance of concrete structures. Design of shear reinforcement? When nominal shear stress tau exceeds the design shear strength of concrete C, shear reinforcement must be designed to resist the excess force. The shear to be resisted by reinforcement is thus equals V tau CB dV underscore us equals V tau underscore C. C deet B. C deet vis equals V tau CBD, where V is the factored shear force, B is the beam width, and D is the effective depth. Shear reinforcement is usually provided as vertical stirrups, bent up bars, inclined stirrups. For vertical stirrups, the spacing S is calculated using S equals 0.87 F, Y asped thus equals F frac 0.87, C dot F, C deta underscore SV, C d dV underscore US S equals thus 0.87 F, Y asp D, where asp equals cross-sectional area of stirrup legs within a spacing. Phi equals yield strength of stirrup bars. The number of stirrup legs and bar diameter is selected to ensure asp is sufficient. The spacing must also comply with maximum limits is less than or equal to 0.75 D or 300 millimeters. Bent up bars and inclined stirrups may also be added near supports for better effectiveness against diagonal cracking. The final reinforcement should ensure that the beam can carry shear loads safely, prevent sudden failures, and provide adequate crack control. Proper anchorage and detailing are equally important for functionality. Critical section for shear as per is code. As per is 456 to 2000, clause 22.6, the critical section for shear in a beam is taken at a distance d from the face of the support, where d is the effect. This location generally experiences the maximum shear force in simply supported and continuous beams. For beams with concentrated loads near supports, critical sections may be adjusted accordingly. Designing at this section ensures the beam can safely transfer loads to supports without diagonal cracking or sudden failure. Accurate identification of the shear critical section is essential for safe and economical structural design. Thanks for watching this in-depth breakdown of shear in RCC beams. We hope this video helped you understand the theory, code provisions, and practical design aspects of shear stress and reinforcement. If you found this content valuable, don't forget to like, share, and subscribe to Civil Engineering Edge for more structural insights. Drop your questions or topic suggestions in the comments. We love to hear from you. Stay tuned for more easy-to-understand videos on concrete design, construction, and civil engineering excellence. Until next time, keep building strong, smart, and safe. Jahind, and happy learning.